So what we're looking here is we're looking into batteries. This is what's going to be our focus today, how batteries work. And as I said, this is one aspect of electrochemistry. This is how important electrochemistry in our life. So different kind of batteries, depending on, again, the applications. And you see this sign, negative and positive, what they mean, and how these batteries produce the outcome, the electricity that we use. So this is what we're going to basically touch on today in this small chapter. So how you can basically look into electrochemistry. Electrochemistry is the area of chemistry concerned with the interconversion of chemical and electric energy. What you're looking at right now, there is a chemical reaction inside these batteries. And this chemical reaction is interconverted into electric energy that basically operate our devices. Once this chemical energy is consumed, the battery is no longer useful. So this is like a one-time battery. There's other batteries like a chargeable batteries, which basically recharge it. So when you charge the batteries, what do? You do the opposite process. And what is the opposite process? The opposite process is basically the electric cell. You put the battery in a charger, that charger is connected to the plug. So you're basically doing the opposite process, where you're converting electric energy is coming from the plug source, into chemical energy. And you are building the battery back again. Then you go back and use the battery again, which is the galvanic. So this is a galvanic cell. So all of these is known as galvanic cell, which they convert chemical energy into electric energy. So our focus today is on the galvanic cell, this part here. How the galvanic cell work, how can you describe what is positive and negative means in terms of electrochemistry? And again, the second part, this is, we're not going to touch on this, but this is the opposite side, which is what we do every day to charge the batteries back again. You look at your cell phone, so you get that meter, that basically indicating how much battery left in your device. As you deplete, as you're using the device, it depletes. And once it reaches a low level, you charge it back again by plugging it in. So by plugging it back, you're basically building the battery back again. So you're doing both of these. The galvanic is when you're not plugging your battery into the wire. Electrolytic is when you plug it to recharge it. So we're going to look into the first part. So how you construct a galvanic cell? You need two different systems. Electrochemistry means you have a cathode and an anode. You have an oxidation and a reduction. So you need these two different processes. In order for an electron to flow, you need these two opposite systems. One system is going to lose the electron, and one system is going to gain the electron. How we decide which one lose and which one gain? Based on the activity of the element. So if you are comparing zinc to copper, if you have zinc coupled with copper, zinc is more active element. Zinc is more active element, which means it's going to dissolve. And that's what you see here. Zinc is converting to zinc ion and giving you electron. And the copper is going to accept the electron. So copper ion here is going to accept the electron and convert to copper solid. So you have two opposite reaction. One is losing electron. The other is gaining that electron that being lost and converting into copper solid. And this is the galvanic cell. So inside of these batteries, you see you have these two reactions happening. One that's cathodic reaction and one is anodic reaction. The anodic reaction is the loss of electrons. This is what happened at the anode, is the oxidation. What happened at the cathode is reduction, which is gaining of electrons. So this is the first fundamental, is what's happening inside the galvanic cell. So how can you construct a galvanic cell? You can build this in the lab. This is a very simple system. You need two beakers. And here's, again, as you can see, a real, real image here to the device. So you have two beakers here. one beaker containing copper sulfate. You can see the blue color here indicate the copper sulfate. And the other beaker contains zinc sulfate, which is a colorless. And you have a zinc metal, which is the electrode for this compartment. And you have the copper electrode, which is again for this compartment. And then you connect them through, we call this crocodile wires. And these crocodile wires are connected to an avometer. An avometer is a device to measure the change in current, resistance, and potential. So we're measuring here the potential, which is basically the potential that raised between these two systems. So this is the actual device. Here is the description for the chemistry. So on the left-hand side here, this is what's happening in the micro scale. So this is the macro scale. What you're looking at right now, you just put two electrodes in two different solutions, in two different beakers, separated and connected by this, again, bridge. And you connect the wires, and then you get the potential. So this is the bulk. So how you get that? How you get that potential 1.1 volt? What is the chemistry of that? Here is the chemistry of what's happening. So on your left-hand side here, you have the two beakers. One beaker contains the copper sulfate and the copper wire metal, which is going to act as the cathode. And the cathode have a positive charge. Then you have the anode, which is the zinc. And the zinc is going to be immersed in zinc sulfate. Zinc is going to dissolve. So once you connect this, you're going to start the electrochemical cell, and the zinc is going to dissolve. Once the zinc dissolves, the electron travels through the wires, as you can see here, to the other side, which is the cathode. And when it goes to the wire, it's now the copper ion will take these electrons and convert to copper solid. So what's happening? You are dissolving the anode. So as the process progresses over time, you're dissolving the zinc. So what's happening to the anode is decreasing in mass. And at the cathode, you are building the cathode. You're putting more copper solid on the cathode. So that means the cathode is getting heavier and the anode is getting lighter. And where this is going to stop? It's going to stop once the anode is completely consumed. So if you go back to these batteries, where this battery is going to die out? This battery will die out once the anode is completely consumed, because you no longer have these two different processes. So this is the one-time batteries. These batteries, you are building the anode back again. So when the anode is consuming, and then you plug it back again in the electric plug, you are building the anode back again. So you recharge in the process. And you just keep back and forth until the lifetime of the batteries is expired. All right. So maintaining again a good, again, like there are some conditions that can basically accelerate the expiration of the lifetime of the batteries. But comparing the one-time batteries versus rechargeable batteries, this is what's happening. The one-time batteries, you cannot recharge the anode. The rechargeable batteries, you can recharge the anodes and build the anodes back again. All right, so one important aspect here, if you don't have this tube, this bridge here, which is this bridge here, if you don't have this bridge, then the ions won't move between the two beakers. And if the ions cannot move between the two beakers, the current will not move. So this salt bridge is very important because what's happening, the electricity is being carried by the ions in solution. You have to make sure that you have this ions mobility between the two solutions. And if you don't have this ion mobility, you won't have this electric current that you see here. So what's in the salt bridge? What's in the salt bridge is a strong electrolyte. That strong electrolyte, its function is to move either to the anode compartment or the cathode compartment to basically neutralize the excess ions. So you have sodium sulfate here. So what's happening to sodium sulfate? This sodium sulfate, the ions are moving between the two beakers. So which ions is going to move to which compartment? Let's look at the anode compartment. What is building up at the anode? You're building zinc positive at the anode. So you're building zinc positive. See, you're producing zinc positive. Why are you producing zinc positive too? Because it's dissolving. This is the oxidation. So at the anode, you're producing zinc ion. At the cathode, you are consuming the copper positive 2 because the copper positive 2 convert to copper. So what do you have? Excess sulfate. So you have excess sulfate at the cathode. So look what's happening. The excess sulfate moves through the salt bridge to the anode. So as a result of that, you have a movement of ions. So the ions are moving between the two beakers. So the sulfate is moving to the anode and the sodium ion is moving to the cathode. And that's why you have this sign. So this sign actually gives you an indication which ions are migrating to which side. So when you see the anode has a negative sign, it has a negative sign because the negative ions are moving toward the anode. And when you see the cathode has a positive sign, that means the positive ions are moving toward the cathode. So you can tell immediately which ion moving between the salt bridge by looking at the sign of the anode and the cathode. So this is very helpful. And instead of memorizing or, again, trying to explain the mechanism of what's happening, you can basically know that from looking at the sign of the anode and the cathode. So the anode has a negative sign because this is where the negative ions migrate towards. The cathode has a positive sign because this is where the positive ions migrate towards. And I explained to you why the negative migrate toward the anodes and why the positive migrate toward the cathode. And here are the two reactions, half reactions. This is the anodic reaction and here is the cathodic reaction. Next is application to the galvanic cell. Number one, how can you determine the cell potential? How you determine this value? And where are you going to get this value from? Which is basically the standard electrode potential. Each of these metals has its own standard electrode potential that is given in tables. So you're not going to memorize anything. You'll be using the standard electrode potential for these metals and basically determine that potential. So this is here to describe each of these, just break down each of these. So what is the anode? The anode is where oxidation occurs. So this is what happened at the anode, oxidation. Is where the electron produced. The electron produced. As I said, this is the slide that I'm going to break it down in the next few slides. So this is the chapter here. I'm breaking down this slide into multiple slides to explain this particular slide. So this one here is explaining what's happening at the anode. Where the anion migrate. Here is the anion migrate towards and has a negative sign. So if you look at any battery right now, you can basically say this is the anode, this is the cathode. Here is the cathode. What's happening at the cathode? The electrode where reduction occurs. The electrode where electrons are consumed. If I go back to this slide, again, we are explaining this side here, this compartment. First of all, cathode is where reduction happens. Here's what reduction is, gain of electrons. Cathode is where, again, the electron migrate towards. The electron are migrating toward the cathode. The cathode is where the ions, the positive ion, migrate towards, or the cations. It's where the cation migrate towards and has a positive sign. So here's the cathode, and here's the anode here. So basically, where is the cathode and where is the anode and what's happening in both compartments? This is here to explain to you why the anion, which is I explained already earlier on. So this is again to explain this. Why the sulfate ion migrate toward the anode? Because you are producing zinc ion. As the oxidation happens, you are producing zinc ion. And as you produce zinc ion, you are building positive. And that's where the negative anion migrate toward to neutralize that excess positive. And here is the cell potential. So this is basically the overall cell. So this is what's happening at the anode. This is what's happening at the cathode. And how many electrons are transferred? 2 electrons. So in this particular galvanic cell, you have 2 electrons transfer. As you can see here, when you balance this, you have to make sure you balance for the number of electrons. So the number of electrons has to cancel out, and that's your overall cell. You can look at this overall cell and you can determine the number of electrons. Look at each one of these. Here's copper positive 2, converted to copper. So how this possible? By gaining 2 electrons. Zinc, convert to zinc positive 2. How this possible? By losing 2 electrons. So this is what's happening, which is the overall cell. So how we write this in terms of notation, like how we write the galvanic cell. So this is how you write the galvanic cell. This is the standard procedure to write the galvanic cell. You start from the anode compartment. So the anode compartment on the left-hand side, the cathode compartment on the right-hand side. You have the salt bridge. This 2 lines here indicate the salt bridge. The first one, the zinc solid, and there's an interface, which is basically the boundary. This is a solid, and this is the aqueous, zinc ion. Then this is the first beaker. Then the second compartment, you have copper positive 2, which is the solution. And then again, a boundary phase, which is the solid. And then you have the copper solid. So this is again explaining this. So far, as I mentioned, we have not covered anything new. We're just breaking down this galvanic cell, breaking each compartment and how each compartment again behaves, and what is the function of the salt bridge, and how you write this in a scientific notation, again, that indicate the galvanic cell. So what I mean a scientific notation, I mean, if I give you a question with something like this, and I ask you which one is the anode, which one is the cathode, and I don't give you any of these information, you can just simply say, this is the anodic compartment because it's on the left-hand side, and this is the cathodic compartment because it's on the right-hand side. This is how we use the standard, again, notation of the galvanic cell. An electron flows goes from the anode to the cathode. So now, how can we determine the cell potential? Because as we said, we are converting chemical energy into electric energy. So how can we measure this electric energy? In order to measure the electric energy, we have to measure the electromotive force, which is the forces that basically move the charges across the 2 anode and cathode, and that's the cell potential. So the cell potential is basically has the unit of, again, volt, and you can convert this unit of volt into joule by multiplying by the charge. So if you multiply the volt times electric charge, you will get the energy. This is how this is very important, because you can look at any device and you can know how much energy that device needs. All what you need is to know the charge, how much charge you have. How you determine the charge? The electric charge is the current times time. I'll repeat, the current times time. I know there's 2 times, but it's current multiplied by time. Here's much better explanation to it. So the charge is I, which is the current, multiplied by the time. And if you look at your charger has a certain current, which is 9 ampere. So you know already what's the charger output current is. You put that charger for 2 hours. So you know your time that you were charging. You can know how much energy you used because you know the voltage. It also will give you the voltage. So you know the voltage and you know the current and you know the time. The time has to be in seconds. So if it's 2 hours, you have to convert the 2 hours to second. And how can you do that? By multiplying by 60 times 60. You know the 1 hour, 60 minutes, and the 1 minute, 60 seconds. So basically, so this is how you measure the energy for, using the charger for 2 hours. Again, so here are the cell potentials for different chemicals. So all of them written in reduction. So all of these are written as reductions, which is all of them given in 1 unit. Why they're all written in reduction? Because the values here mean, again, a very important outcome. If this is positive, the more positive it is, the more cathodic it is. So the positive is going to be the cathode. So if you're comparing 2 numbers, the more positive is going to be the cathode. So if you're mixing these 2, if you have one compartment has fluorine and one compartment has hydrogen peroxide, Which one is going to be the cathode? Which one is going to be the anode? The cathode is going to be the more positive one. And as you go down, you can see, you can compare any values here and you can tell the more positive is going to be the cathode compartment. The less positive is going to be the anode compartment. How about if you're comparing two negatives? The same way, the less negative. So if you're comparing these two, the less negative is going to be the cathode compartment and the more negative is going to be the anode compartment. So always you're looking into toward the more positive. Whoever is more in terms of positive, of course, the less negative, you're going toward the positive direction, as you can see here. So looking at this table, basically, whoever is above is going to be the cathode. Whoever is below is going to be the anode compartment. So why it's important to identify the cathode and the anode? Because in order to identify the cell potential, you need the difference between the cathode and the anode. So how we measure these values? We measure these values by using the galvanic cell one more time. Instead of having and we have a reference, again, electrode, and that reference electrode is hydrogen. So we use hydrogen as a standard potential because hydrogen has zero standard potential, as you can see here. So whatever you're measuring here is going to be the potential for the other compartment. So if I couple hydrogen with copper, it read 0.34. If it read 0.34, then this is the copper standard electrode potential. So anything above hydrogen, whatever reading you're going to read is going to be positive. Whoever below hydrogen, whatever reading you're going to read is going to be taking negative sign to it. So that will be negative, whatever the value is here. So if this was lead, for example, if this was lead here, and then with the potential is negative 0.13. Why? Because it's below hydrogen, as you can see, which means this is the anode and hydrogen is the cathode. If it's above hydrogen, it's positive. If it's below hydrogen, it's negative. So this is how we constructed this standard electrode potential table using the hydrogen reference electrode in this case. So how you measure the cell potential? Cathode minus anode. And this is why it's important to identify the cathode and the anode. So if I give you any compartment, out of these, and I ask you to calculate the cell potential, all what you need is cathode minus anode. Cathode minus anode. So all what you need is the cathode minus anode. That's why you need to know where is the cathode and where is the anode. And you're going to know from the cell potential. So here are different examples. Zinc and copper. How are we going to measure the electrode potential, the cell potential for zinc and copper? Let's go back to the table. Where is copper? Here is copper, positive 0.34. Where is zinc? Here is zinc, negative 0.76. Cathode minus anode. Cathode, copper is the cathode. Why copper is the cathode? It's more positive. It's above. Zinc is below, negative. So cathode minus anode. Minus minus, it becomes positive. That's why you see this positive here. Minus minus. So this is basically positive, and this is how we get 1.1 volt. Still on here, we're explaining this. Why? How you get 1.1 volt. And you get 1.1 volts because you have cathode minus anode. The cell potential for the cathode minus the cell potential of that. Here is the copper. Here is the cell potential for the copper, electrode potential for the copper. Here is the zinc. Here is the electrode potential for the zinc. And again, when you add both, again, cathode minus anode, this becomes positive. So the negative is going to be flipped here because cathode minus anode. Let's look at another example, silver and copper. So silver and identify the cathode and anode. Where's silver? Here's silver. Where's copper? Here's copper. So if I ask you right now, who's the cathode and who's the anode? Silver is going to be the cathode. Copper is going to be the anode. So in this case, cathode minus anode. Here's the cathode. Here is the anode. Again, this is how you do the calculation. We are measuring the standard cell potential. We are measuring everything in standard condition, under standard condition. Related to the free energy of the system through this equation. So delta G, if you recall from chapter 18, free energy of any given chemical or physical change in electrochemistry is equal to negative N, which is the number of moles of electron transfer, times Faraday constant times the cell potential, which we already know how to determine that. This cell potential, we just did cathode minus anode. So if I go back to this, here is the cell potential for this system. Here is the cell potential for this system. So I already know E. What is F? F is Faraday constant, which is the number of charge per 1 electrons, per 1 mole of electrons. So if you have 1 mole of electrons, this is 96,500 coulomb. This is the amount of electricity from 1 mole of electrons, which is 96,500. So I have already F, which is Faraday constant. What's missing right now is N. Where are you going to get N from? Remember, N is the number of electron transfer. So how do you know the number of electron transfer? Look at any of these elements. Compare the left-hand side, the reactant side, to the product. Copper 0, copper positive 2. So how many electrons are being moved? 2 electrons. The same thing here. Copper positive 2, taking 2 electrons. So you can tell from looking at the number of electrons. Look at silver. Here there are 2 silver ions, and that's why you need to multiply by 2 because there are 1 electron only here. And very important point here. This is not an additive. The standard electrode potential is not an additive. What I mean by that? I mean, this has nothing to do with the number of electrons here. So if you multiply this by 2, if you multiply this by 3, if you multiply this by 4, the standard electrode potential will not change. So again, so this has nothing to do with, again, the multiplication. It's not like energy. Energy is an additive. Delta H is an additive. So you change, you multiply the chemical reaction by a coefficient, you multiply delta H by the same coefficient. For electricity, this is not the case. The standard electrode potential doesn't depend on how many number of coefficients you multiply the equation with. All right. So again, this 0.8 is for silver here from the table. So all I'm trying to say, this numbers here will not change for these reactions if you multiply them by any coefficients. So that's what I'm trying to say. Any of these standard electrode potential are independent on the coefficients that you multiply these equations with. So when you're balancing the chemical reaction, it doesn't matter what the coefficient multiplier is, these values will not change. So I hope I got my point across. And this is what it says intensive. Intensive means it doesn't depend on amount, it doesn't depend on how many you multiply with. All right, so this is how we use this equation. The difference between these two, that this is under standard condition. When you see the node on the top here, or the circle here, that indicate a standard condition, which is 1 atmosphere and 1 molar. The concentration has to be 1 molar, and the temperature has to be 25 degrees Celsius. So this is the standard condition. So here's an example. Calculate the delta G for this galvanic cell. If the cell potential is 1.1 volt, the temperature is 25 degrees Celsius, which is a standard condition, as I mentioned. So basically using, again, what we know, the number of electrons are 2, zinc 0, 1 to zinc positive 2. F is Faraday constant. E node is 1.1 volt, dividing by 1,000 to convert it to kilojoule. So your outcome is going to be negative 212 kilojoule. So this is why we divide by 1,000 to convert this from joule to kilojoule. So in this case, this is the highly spontaneous. Remember, when delta G is negative, the reaction is spontaneous. So you can apply the same concept that we learned in chapter 18. As I said, chemistry is interconnected. So we went from a thermodynamic point of view to how to use electrochemistry to determine the free energy of any given system. So if you have any given system that you can measure in a galvanic cell, you can find the free energy of that system. And if you determine the free energy of the system, you can determine the equilibrium constant. This is how powerful these models are. From determining the free energy, you can determine the equilibrium constant.